Imagine looking up at the night sky and witnessing a breathtaking display of vibrant, dancing lights. These are the auroras, celestial ballets of green, purple, and red that often grace the polar regions. In the northern hemisphere, these luminous light displays are known as the aurora borealis, or the northern lights, and recently they have been visible far further south than normal. In the southern hemisphere, they are known as the aurora australis, or the southern lights. These mesmerizing lights have been spotted in places they don't usually belong, captivating sky watchers far beyond the Arctic and Antarctic circles. These unusual sightings are a stunning reminder of the sun's immense power and its ability to reach out and touch our planet in extraordinary ways. But what causes these celestial displays? The answer lies in the heart of the sun and the fascinating phenomenon of solar storms. These auroras, while beautiful, are a visible consequence of a much more powerful event: solar storms. These storms, eruptions of energy from the sun, send charged particles hurtling towards Earth. Our planet's magnetic field deflects most of these particles, but some are drawn towards the poles. Earth's magnetic field is known as the magnetosphere, which acts as a shield, deflecting most of the solar wind. However, near the polar regions, the magnetic field lines converge and allow some of these particles to penetrate the atmosphere. As these charged particles enter the upper atmosphere, known as the ionosphere, they collide with gas molecules like oxygen and nitrogen. These collisions excite the gas molecules, raising their energy levels. When the excited gas molecules return to their normal state, they release the excess energy as light, creating the dazzling light show we call the aurora. Oxygen emits green and red light, while nitrogen can produce blue and purple hues. Solar storms are powerful bursts of energy from the sun. They occur when the sun's magnetic field lines become twisted and tangled, like a rubber band wound too tight. This buildup of energy is eventually released in a sudden, explosive event, sending a surge of charged particles, known as solar wind, out into space. The solar wind is a stream of charged particles, primarily plasma, that is continuously emitted from the upper atmosphere of the sun, known as the corona. It plays a crucial role in shaping space weather and influencing planetary magnetospheres, including Earth's. The solar wind is made primarily of protons, electrons, helium nuclei, and other ions. Protons are the most abundant component, which are positively charged hydrogen nuclei. Electrons are negatively charged particles, while helium nuclei, also called alpha particles, consist of 2 protons and 2 neutrons. Other ions include heavier ions like oxygen, carbon, and nitrogen, and are present in smaller quantities. The intensity and frequency of these storms are directly linked to the sun's 11-year cycle, a period of fluctuating solar activity known as the solar maximum. The solar cycle is driven by the sun's magnetic field, which undergoes periodic changes, influencing solar activity levels. During solar maximum, the sun is at its most active, with sunspots, solar flares, and coronal mass ejections occurring more frequently and with greater intensity. During solar maximum, flares are more frequent and can affect Earth by disrupting communication systems, causing radio blackouts, and enhancing the radiation environment for spacecraft and astronauts. Coronal mass ejections are massive bursts of solar wind and magnetic fields ejected from the sun's corona. During solar maximum, CMEs are more common and can result in geomagnetic storms when they interact with Earth's magnetosphere. These storms can produce beautiful auroras and stunning light displays, but they can also disrupt satellites, GPS, and power grids. These events can have significant impacts on Earth and other planets in our solar system. Understanding solar storms and their connection to the Sun's activity is crucial for predicting and mitigating their potential effects on our technology-dependent world. The recent appearance of auroras in unusual locations is a testament to the power of particularly strong solar storms. Typically, auroras are confined to the polar regions due to the Earth's magnetic field lines. However, during intense solar storms, the surge of charged particles can penetrate deeper into Earth's atmosphere, pushing the auroral ovals further towards the equator. This expansion allows people living in lower latitudes, who might never have witnessed the northern or southern lights before, to catch a glimpse of this celestial spectacle. While these unexpected displays are a visual treat, they also serve as a reminder of the Sun's influence, extending far beyond what we typically perceive. Solar activity can also cause more widespread ripples through space and affect our planetary neighbours. The Sun's influence, therefore, isn't limited to Earth. Solar storms, with their bursts of energy and charged particles, ripple through the solar system, impacting every planet in their path. While Earth has its magnetic field to shield it, other planets experience the effects of solar storms in different ways. Some planets, like Mars, have weaker magnetic fields, offering less protection from the Sun's wrath. Others, like the gas giants, have powerful magnetic fields that interact with solar winds in complex and fascinating ways. Understanding how solar storms affect different planets provides valuable insights into the dynamics of our solar system and the unique characteristics of each celestial body. Our closest planetary neighbour, the red planet Mars, feels the effects of solar storms in a more dramatic way compared to Earth. Mars, our smaller, red neighbour, lacks a global magnetic field like Earth's. This lack of protection makes it particularly vulnerable to the effects of solar storms. Without a global magnetic field to shield it, Mars is exposed to the solar wind and the energetic particles from solar storms. When charged, particles from the Sun reach Mars, they interact directly with its atmosphere, stripping away molecules and contributing to atmospheric loss. These charged particles strip away the upper layers of Mars' atmosphere through a process called sputtering, where high-energy particles knock atmospheric atoms into space. This process has significant implications for the possibility of liquid water and life on the red planet. The mission of the Mars Curiosity rover, launched on November 26, 2011, part of NASA's Mars Science Laboratory, was to explore the surface of Mars with the primary goal of determining whether the planet has ever had the environmental conditions necessary to support microbial life. Curiosity has discovered evidence of ancient lakes and rivers in Gale Crater, confirming that Mars had liquid water in the past. The continuous exposure to solar storms and the solar wind over billions of years is thought to be a key factor in the gradual loss of Mars's atmosphere and surface water. The stripping of the atmosphere makes it harder for the planet to maintain surface water, contributing to the arid conditions we observe today. In 2017, NASA's MAVEN, Mars Atmosphere and Volatile Evolution mission, observed a massive solar storm that caused a dramatic increase in the density of the ionosphere, temporarily disrupting communication with Mars rovers. Understanding how solar storms have shaped Mars's atmosphere over time is crucial for unraveling the planet's past and informing future missions to search for signs of ancient life. solar storms pose a significant challenge for future human missions to Mars. During a solar storm, astronauts on the surface or in transit would face heightened radiation exposure, which can increase cancer risks and damage biological tissues. Effective shielding or shelters would be needed to protect humans during such events. The solar wind has a profound impact on the entire solar system, shaping space weather, planetary environments, and interplanetary magnetic fields. It interacts with the planets, erodes atmospheres, affects radiation levels, and influences the frequency and magnitude of dazzling planetary auroras, making it a fundamental aspect of the solar system's dynamics.